When an object is stretched or compressed elastically, work is done to give the object elastic potential energy. For example, think of launching an elastic band. When the band is stretched, the body does work on the band, converting chemical energy into elastic potential energy. When the object is released, this elastic potential is converted to kinetic energy. So when we release the band, the elastic potential energy turns into kinetic energy. The band then suddenly gains velocity. So what can we say about the relationship between elastic potential and kinetic energies? Well, assuming no energy is lost to the surroundings, the kinetic energy gained upon release is equal to the elastic potential energy stored during deformation. But this isn't the case for inelastic deformations, as some of the energy is used to break bonds. So elastic potential energy stored is equal to kinetic energy gained. The elastic potential, EE, is equal to half KE squared. Remember that the equation for elastic potential energy only applies below the limit of proportionality. The kinetic energy, EK, is equal to half mv squared. So we know that EE is equal to EK, so we can say that half KE squared is equal to half mv squared. We can then also cancel out the halves to simplify the equation further. You don't need to be able to perform this derivation. You can also calculate the energies separately in exam questions. Let's have a look at an example. A 0.6 kilogram stone is pulled back on a slingshot with a light elastic band, giving it 66 joules of elastic potential energy. Calculate the speed at which the stone will be launched when released to two significant figures. So we can round our answers to a certain number of digits, and the number of significant figures are the number of digits in the value. So in this question, we can assume that the stretching is elastic and the mass of the band is negligible. So for the first step, let's write down the key information and check the units. The mass is equal to 0.6 kilograms, and the elastic potential energy is equal to 66 joules, and we want to calculate the speed of the stone. For step 2, let's determine the kinetic energy given to the stone. So we can assume that all of the elastic potential becomes kinetic energy in the stone. So the kinetic energy given to the stone is 66 joules. For step 3, let's rearrange the kinetic energy equation so that only v squared is on one side. So we can rearrange this equation algebraically. We must do the same action on both sides of the equation, and we can also swap around the two sides. So we can start by multiplying both sides of the equation by 2 to give 2ek is equal to mv squared. We can then divide both sides of the equation by m, and that gives us 2ek divided by m is equal to v squared. Then swapping the sides, we get v squared equals 2ek over m. For step 4, let's take the square root of both sides to make speed the subject of the equation. So it was important to bring v squared to one side first, as we must take the square root of the whole side, not just one term. So v is equal to the square root of 2ek divided by m. For step 5, we need to substitute the values to calculate the speed. So v is equal to the square root of 2 times by 66 joules divided by 0.6 kilograms, and that is 14.832 meters per second. For the final step, all we need to do is round to two significant figures. So the first significant figure is 1 and the second significant figure is 4. The next value is 8, so we can see that we need to round the second significant figure, and that gives us 15 meters per second.
Thanks for watching. If you want to take your GCSE revision to the next level, head over to launchpadlearning.com and check out our smart learning platform that's been designed to get you top results in your exams. We cover your whole specification and make revision fun with interactive quizzes, easy to follow videos and more. You'll be kept motivated by your own AI tutor who's here to support you every step of the way. To check it out for yourself, click here. Or click here to keep watching a selection of the videos from our full GCSE Physics course. See you there!